channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. आज हम केमिस्ट्री की क्लास करने वाले हैं जो कि 144th क्लास है. ऑलरेडी हमने 143rd क्लासेस कर लिया है जिसमें हमने लैटिस एंथैल्पी से पहले की जो कि एंथैल्पी ऑफ द सॉल्यूशंस जो डिस्कस किए थे वो लास्ट टॉपिक हमने डिस्कस किया था. In this class, we'll start discussing about the lattice enthalpy. That is also an important topic in reference to the competition wise if I'm talking about. So lattice enthalpy, first of all, starting with the lattice enthalpy of the class of 144. Before that, it's a request, अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, इट्स अ ह्यूज रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब कर लो so that many and maximum people के पास वीडियोस पहुँचे. And even though you can also utilize those videos for that learning all these topics what we are offering in the case of the thermodynamics related to NCERT here. So lattice enthalpy, what is lattice enthalpy here? The lattice enthalpy of an ionic compound is the entirely change which occurs when 1 mole of an ionic compound dissociate into ions in the gaseous state. So lattice enthalpy क्या होता है? Basically lattice enthalpy एक ionic compound की enthalpy change जो होती है जब अकर होता है 1 मोल ऑफ आयनिक कंपाउंड जब डिसोसिएट होता है आयंस में गैसेस के फॉर्म में, then that is known as the lattice enthalpy here. If I'm talking about this, so you can just run through with Na plus Cl, that is a salt. You also know that is in the form of solid, and when it dissociates, even the lattice enthalpy takes place. So it just break in N plus, that is in the form of the gaseous ions, and that is Cl minus, that is also in the gaseous with minus sign. Lattice enthalpy जो उस टाइम पे होगी, that is for the NaCl is plus 788 kilojoule mole inverse here. With reference to this, if I'm talking about with regard of this, we can say that since it is impossible to determine the lattice enthalpy directly by the experiment, we use an indirect method where we can construct the enthalpy diagram, and that is called a Born-Haber cycle. This is what we called as. For the Born-Haber cycle, let us now calculate the lattice enthalpy of Na plus Cl minus, that is in the solid state, by following the steps given below here. With regard of that, if I'm talking about the Na, that is in the form of the solid, and that is gives the Na in the form of the gases here. With reference to this, this is the sublimation of sodium here, sublimation of the sodium metal, and where the sublimation enthalpy that we will give is 108.4 kilojoule mole inverse. This is the sublimation of the sodium metal here. With regard of the second one, that Na, that is in the gaseous form, and gives Na plus, that is in the form of gas, and that is of leave of 11 electron here. In reference to this, the ionization of the sodium atoms, ionization enthalpy, and where ionization enthalpy, that will get it for 496 kilojoule mole inverse. Regard of the third one, if I'm talking about, that is half of Cl2 gas, that gives the Cl gas in the form of the gas here. And if I'm talking about, this is the dissociation of the chlorine reaction enthalpy is half of that particular, if I'm talking about, so that is a half of the bond dissociation enthalpy. So we can just write it down that half of bond enthalpy equals to 121 kilojoule mole inverse. Regard of this, if I'm talking about further, moreover, if I'm discussing all these ionization enthalpies as well as related to the lattice enthalpy, with regard of that, if I'm talking about the next reaction, that is your Cl, that is in the form of the gas plus adding 1 electron, and that gives the Cl gas here, and that is the if I'm talking about this, the electron gained by the chlorine atom, and the electron gain enthalpy that will get here is your minus 348.6 kilojoule mole inverse. With regard of that, we know that the ionization enthalpy of that electron gain enthalpy, and even though in terms of, in fact, we can say that these terms have been taken from the thermodynamics, and earlier terms, ionization enthalpy, energy, and the electron affinity were in the practice in place of the above terms, and that we can say that the ionization enthalpy and the electron affinity, if I'm talking about, that is also an important topic related to this only, related to the ionization enthalpy and the electron affinity. Ionization enthalpy and the electron affinity are defined at absolute zero at any other temperature, heat capacity, or you can say that the reactant and the product have to be taken into account. So the enthalpies of the reactions, for that sake, we will be having a forming like and that is in the form of the gas state, it will gives M plus, and that will be E. This is for the ionization. And for the next one, that Mg, and that is a plus of a electron, and that gives your M a minus, that is of G, the electron gain, that is at temperature T here. With regard of that, we can say ahead. Moreover, if I'm talking about the change, the temperature change, that is H of means like of reference to the temperature, so we can say that that is equals to delta R of H enthalpy, that is of 0. And even though that is plus, that is 0 से लेके t तक, and that is delta R Cp, and this is of delta T here. And where the value of Cv for each of the species in the above reaction is what you can say, I can write it on here, that is like 5 by 2 R, and that is where Cv is equals to, you can say that 3 by 2 R here. Okay, so this is what the the each species, the value of the Cv we have. And reference to that, we can say that delta C of V, that enthalpy is plus 5 by 2 R for the ionization, and for the Cv with reference to the electron gain, so we'll get minus 5 by 2 R here. Therefore we can say that delta R of that H ionization enthalpy is equals to the ionization enthalpy plus 5 by 2 RT, and that I will write it here. And after that we have a delta R, that is of H minus electron gain enthalpy, so we'll have minus A, that is of electron affinity, and minus 5 by 2. That I will write it down here. You can just write it on those things that is important related to the ionization enthalpy as well as the electron affinity here. So what I had told you, that I had made you write is delta R of H, that is abstract, and that is ionization enthalpy, and that is equals to your that is E naught that is plus by 5 by 2 RT, and with reference to the delta R of H, and then that is for electron electron enthalpy, electron gain enthalpy, then that is equals to minus A, which is electron affinity, and as well as that is minus by 5 by 2 RT. So this is what I am talking about, and what I had told you. And this is the diagram representation here, that is enthalpy diagram for the lattice enthalpy NaCl. Here this is Na plus, and this is gas plus a Cl. This is in the state of gaseous here, where at this is Na plus gas and half of Cl2. Where it goes to it, that is half delta bond enthalpy, and that is 121 kilojoule mole inverse. When it returns to it, a delta, that is of the enthalpy we have is minus 348.6 kilojoule mole inverse, and it goes gives as Na plus G, that is in the form of the gas state, plus a Cl, that is often also in the form of the gas state. When I'm talking about the Na, that is in the form of the gas state plus a half of Cl2 here on the gaseous form, and that the enthalpy with respect to the temperature here, that will be the plus 495.6 kilojoule mole inverse. With regard of this, the Na that is in the form of solid, and half Cl2 that is in the form of gas, it will give the sublimation enthalpy that we have is plus 109.4 kilojoule mole inverse. With regard of this, if I'm talking about, so this is the NaCl that is in the solid, and where it gives that lattice here, and that is the fusion enthalpy we have is minus 411.2 kilojoule mole inverse. This is the enthalpy diagram for the lattice enthalpy of the NaCl, that what we are discussing about it. Now moving ahead with the fifth point related to the lattice enthalpy that we have to discuss here. Here, this is the fifth one is Na plus, that is in the form of the gas state, and the Cl minus, that is in the form of the gas state, which gives Na plus Cl minus in the form of this, that is in the form of the solid state here. With regard of this, if I'm talking about the sequence of these steps is what I had write it down, and is known as Born-Haber cycle. The importance of that cycle is that the sum of the enthalpy in changes around a cycle is 0. So applying there, we are applying here Hess law that we had discussed here. So we are applying the Hess laws, and that we will get for that applying, and then we'll get that is of delta the lattice H minus, that is equals to 411.2 plus 108.4 plus 121, and then we have plus 496, and then minus 348.6 here. With regard of this delta lattice, what we're finding out, the lattice enthalpy is plus 788 kilojoule here. And for the NaCl, if I'm talking about, so here Cl it will give Na plus with in the form of the gas state, as well as Cl minus, that is in the form of the gas state as well. The internal energy is smaller to by 2 RT, that is because that delta n of g, that we can say that that is equals to 2, and that is equals to plus 783.783 kilojoule mole inverse. So now we use the value of the lattice enthalpy to calculate the enthalpy of the solution from the expression. So we can just write it down here like delta sol H minus, and that is equals to delta lattice here, and that is of H minus and plus delta hybrid of H minus here. So for 1 mole of the NaCl, the lattice enthalpy will be here plus 78 point kilojoule mole inverse, and delta that is of that is if I'm talking about the hybrid form, and that will give the for the hybrid it will give u minus 78 784 kilojoule mole inverse from the if I'm talking about the written method. So we'll just find it out the delta solubility here. Okay, so delta solubility of enthalpy will get a plus 788 and a kilojoule mole inverse, and that is minus 784 kilojoule mole inverse here, and we'll find it out and get 4 kilojoule mole inverse, and that is the dissociation of the NaCl is composed by a little heat change as well. So with reference to the NaCl here. So moving ahead with the spontaneity, and that is also an important topic reference to the NCERT. So the spontaneity, if I'm talking about the spontaneity, so we'll discuss some of the things that the first law of the thermodynamics that tell us about the relationship between the heat absorbed and the work performed on or by the system, that it puts no restrictions on the directions of heat flow, and however the flow of the heat is unidirectional from the higher temperature to the lower temperature. In fact, all the naturally occurring process, whether a chemical or a physical, will tend to the powered that proceed to the spontaneous in one direction, as well as that will tend to the proceed spontaneous in one direction and only. And for example, like gas expanding to fill the available volume, burning carbon in dioxygen giving a carbon dioxide, as well as in return of that, if I'm talking about but heat will be flow from colder body to the warmer body on its own, and the gas in the container will not spontaneously contrast and into one corner to the carbon dioxide, corner से दूसरे carbon dioxide will not form a carbon and dioxygen spontaneously. These and many other spontaneous occur changes to show the unidirectional change. We may say that what is the driving force of the spontaneity occurring the changes, what determines the direction of the spontaneous change, and in this we will discuss about the criteria proceed whether these will take place or not. So let us understand like what do we be the spontaneous reaction or change would be, and according to that we will take it up like the case of the combination of hydrogen and oxygen, if I'm talking about this. So these gases may be mixed at a room temperature and left for many years without observing any perceptible changes, and although the reaction is taking place between them, it is an extremely slow rate, and it is still called the spontaneous reaction as well. Okay, and then the spontaneity means is having the potential to proceed without the assistance of the external agency, and however it does not tell about the rate of the reaction or process, and that another aspect of spontaneous reaction here or a process, as we see that these cannot be reversed their reactions on their own, and we may summarize it as like that what we had written here, the spontaneous process is an irreversible process. The spontaneous process is known as the irreversible process and may only be reversed by the some external energy agencies. These that the spontaneity is stands for. With regard of spontaneity, the first part will be the is a decrease in the enthalpy, a criteria for the spontaneity. If we assume this, so we examine the phenomena like a flow of the water downhill and fall of a stone onto the ground, and we find that there is a net decrease in the potential energy in the directions of the changes. By analogy, we may attempt it that that the state that is a chemical change reaction and the spontaneity of that given direction, because decrease in the energy has take place as in the case of the exothermic reaction. For example, if I'm talking about the half N2 gas, and that is mixed with 3 by 2 H2 gas, and that will get NH3 here. Okay, that's enough of the gas. And the enthalpy for the spontaneity that we have is minus 46.1 kilojoule mole inverse. And then we take another equation here, as well as the half H2 gas and plus half of Cl2 gas in the form of the gas, and that will give the Cl gas, and that the enthalpy we have is minus 92.32 kilojoule mole inverse. And in regard of H2, if I'm talking about H2, that is in the form of the gas state, and plus of half of O2 gas state, which give H2O in the form of the liquid state, and that delta R of enthalpy is minus 285.8 kilojoule mole inverse. With regard of this, if I'm talking about the decrease in the enthalpy in passing from the reaction to product, may be shown by the exothermic reaction on an enthalpy, which we'll discuss in the enthalpy diagram as well. And there's the postulate that driving from the forces of the chemical reaction may be due to the decrease in the energy sound that is reasonable, of course, on the basis of the evidence so far. So now let us examine the following reaction, that is your half N2, that is in the form of gases, plus O2, that is in the form of gas, and then get NO2 gas in the form, and that is of delta R of H, or we'll get plus 32.2 kilojoule mole inverse here. With regard of this, we'll discuss the enthalpy diagram for the exothermic reaction as well as the enthalpy diagram for the endothermic reaction. And before that, we'll study one of the reaction related to the graphite, which will be in the form of the carbon here. Here the carbon that is in the form of the graphite, and that is in the form of solid, of course, and that plus 2 that is 2SR and that is in the form of liquid, and that give CS2 that is in the form of the liquid, and the enthalpy that we will get is plus 128.5 kilojoule mole inverse. This is the enthalpy that it gives. So as I told you that we'll discuss enthalpy diagram for the exothermic reaction. So this is a diagram which will discuss the enthalpy diagram for the exothermic reaction. This is the reaction which is H, and this is the reaction that is reaction coordinate. This is the reactant, this is a product, as well as if I'm talking about this is the total enthalpy of the product, that is denoted by HP, and the total enthalpy of the reactant, that is denoted by the HR. This goes further than out, and this is for the product here, and this is reference to the net heat evolved in the reaction. This is the gap that denotes it. If I'm talking about the enthalpy diagram for the this is for the exothermic, we'll discuss about the endothermic. So here you can see that the endothermic as well, as you can see, and as you can go through with it, you will be getting all that enthalpy diagram for the endothermic reaction as well. So this is the total enthalpy of the product, that is denoted by the PHP. Here it is in the downward, and for the total enthalpy of the reactant, that is represented by the HR and H of R, and that is by a dotted line, and this is a product. There is a reactant, so it will be here, and this is product, so it will be here. So this is the net heat absorbed from the surrounding in this reaction, and this is the enthalpy diagram for the endothermic reaction, if I'm talking about. So these reactions through the endothermic, or the spontaneity and the increase in the enthalpy, may be represented on the enthalpy diagram that we had discussed here. And this it becomes the obvious that while the decrease in the enthalpy may be contributory factor of the spontaneity, but it is not true for all the cases that we have to discuss here. So in respect to that, we'll discuss the another topic, and that is your entropy and the spontaneity here. So in terms of entropy and the spontaneity, if I'm talking about, you have to know before this you have to know some of the points related to the entropy and the spontaneity here. Okay, so with reference to the entropy and then spontaneity, then what drives the spontaneous process in a given direction? Let us examine such a case in which the delta H equals to 0, where there is no change in the enthalpy, but still the process is spontaneous. So let us consider the diffusion of two gases into each other in a closed container, and that will be the isolated from the surrounding, as we will discuss. Like this is a figure here. I can write it down for the spontaneity and of course for the entropy. There is this is a container, sort of a container here, and where it will be participated, it is a partially break-in here, and यहाँ पे कोई different gas है, for example, and यहाँ पे there is a different gas. I will be just marked with the blue here so that you will get it out. So यहाँ पे different gases. This is the combination, that is the diffusion of the gases, of the two gases. They are the two gases that is separated by a a panel here. So but with another diagram where we're talking about the diffusion of the two gases here. So here we have this partition, as we can see that there is the two different gases. So here one will be this, the gases is present in with the black and the blue, which I had mentioned here with the another gases. So this is also present in between, with mixed with each other. So this is what the diffusion of the two gases stands for, and what we can say in reference to that. The two gases say that, like, get A and B, gas B, we can say that represented by the black dots, and that is the blue dots respectively. So that is separated by movable partitions, and when the partition is withdrawn, the gases begin to the diffuse into each other, and after a period of time diffusion will complete. Let's examine the process before partition. If we were in pick up the gases molecule from the left container, we would assure that these will be the molecules of the gas A. And if I'm taking if you are separating, similarly we'll do that same thing from the another end. So we'll pick up the gas molecule from the right container. We would sure be that this will be the molecule of the gas B. But if we will pick up the molecules from the container when the partitions is removed, as you can see here, so we are not sure whether the molecules that we have picked up, that is of gas A or B, we can say that the system has been becoming a less predictable or more, that is chaotic. So if I'm taking over from this, so we'll get okay, this is the gas A. If I'm taking from the this, we'll get okay, this will be the gas B. But with the case of this, we not identify gas B like gas area, so we don't that makes not less predictable and as well as more chaotic here. So we will formulate another postulate. Is an isolated system, there is always a tendency for the system that energy to become the more disorderable or chaotic, and this could be the criteria of the spontaneous change as well. At this point, we can introduce another thermodynamic function, that is entropy, denoted that entropy is denoted by the S here. And the above mentioned disorder is to the manifestation of entropy, and to form a mental picture on one can think entropy as a measure of the degree of the randomness or disorder in the case of the system. And the greater the disorder in the isolated system, the higher the enthalpy is. And as far as the chemical reaction is concerned, this entropy change can be attributed to the rearrangement of that atoms of ions, and from one partition into the reactants to the another in the product here. So we are reacting to another, that is in the product, and if the structure of the product is very much disordered than that of the reactant, and there will be resultant increase in the enthalpy. The change in the enthalpy accompanying a chemical reaction may be estimated qualitatively, and by the consideration of structures of that species taking a part in the reaction, and decrease of regularity in structures would mean increase in the entropy. And for a given substances, the crystalline solid state is a state of the lowest entropy, and the most ordered, that would be the gaseous state is still a state of the highest entropy as well. So we can say that now let us try to quantify the entropy. One way to calculate the degree of the disorder of the chaotic distribution of energy among the molecules would be those statistical method, which is beyond the scope of the statement. Another way would be to relate this process to the heat involved in the process, which would make the entropy a thermodynamic concept. Entropy, like other thermodynamic properties such as internal energy, that is represented by U, and the enthalpy H, and as a state of function of the delta S. So the independent of that path, we can say that whenever the heat is added to a system, it is increase the molecular motions, causing increased randomness in the system, and thus heat that is represented by Q, and that has been random influence on the system. And can we then equate delta S with Q. And so for this system at a higher temperature has a greater randomness in it, and then one at a lower temperature. Thus, the temperature is the measure of the average chaotic motion of the particle in the system, and heat added to a system at a lower temperature causes greater randomness than when the same quantity of heat is to be added to its higher temperature. And we can say that this suggests that the entropy change in the inversely proportional to the temperature, that is delta S is related to the Q and the T, and for the reversible reaction. So for that reversible reaction, the delta S equals to Q reversible upon T here. That is the total energy change of delta S, which that total for the system, for the surrounding of the spontaneous process, that is given by like delta S total is equals to delta that is of S, that is of system, and delta S of the surrounding, that is greater than 0 S cos, and that will it represent like this. And when a system is in the equilibrium, when the entropy is maximum, and the change in the entropy, that will be the delta S equals to 0. So we can say that the entropy of for spontaneous and for the spontaneous process increase till it reaches to the maximum and equilibrium, the change of the entropy is 0. And since the entropy is in the static property state of property, and then we can calculate the change in the entropy of the reversible process by like delta S of system equals to that is Q system reversible, and that is upon 3. So this is what it represents here, and according to that we find that both for the reversible and the irreversible expansion for an ideal gas under the isothermal condition, that is delta U equals to 0, and but we can say that delta S total, that we can find it out delta S system plus delta S surrounding, that will have a delta S total here, we can see that. And it's not to for the irreversible process, thus delta U does not discriminate between the reversible and the irreversible process, whereas delta S does this. Okay, so with regard of this, we will move ahead with some of the question. As I told you, we'll discuss and we'll hopefully will end up with this session in this class only. So the question we have is predict in which of the following entropy increases or decreases. आपको predict करना है कि किसमें आपका entropy जो है वो increases करेगा या फिर decrease करेगा. For our first question here, a liquid crystallize into solid. जब liquid जो है वो crystallize करता है solid में, for this we can say that after freezing we can just I can just write it down here. After freezing, the molecules, so that is the after freezing the molecules attain that an ordered state, and therefore entropy decreases. Okay, so a liquid crystallized into a liquid, you can just answer that after freezing the molecules attained an ordered state, and therefore the entropy decreases. Yeah, the second will be the temperature of crystalline solid is raised from 0 Kelvin to 115 Kelvin here. For this, if I'm talking about, so at 0 Kelvin, if I'm talking about at 0 Kelvin, the conditions of the particles are static and the entropy is minimum. And if the temperature is raised to 115 Kelvin, these begin to move and oscillate about their equilibrium position in the lattice and the system that becomes more disordered, therefore the entropy increases in this case. So we will go ahead and just write it down. You can just write it down here also. At 0 Kelvin, the constituent particles are static and entropy is minimum. If temperature is raised to 115 Kelvin, then these begin to move, that is begin to move and oscillate about their equilibrium position in the lattice and the system, in the lattice and system becomes more disordered, therefore entropy increases. Okay, so this is for the temperature. The temperature of the crystalline solid is raised from 0 Kelvin to 115 Kelvin. So it will, the entropy will be increased and liquid crystallized into solid. So the entropy will be decreased. So for the third question, we will go ahead. So the equation we have, the third one, we have 2NaHCO3 that is in the form of solid, and that gives Na2CO3 solid, and that is carbon dioxide gases, and the H2O that is in the gaseous form here. With regard of this, the reactants NaHCO3 that is solid, and it has a low entropy, and among the product there are one solid and the two gases, so there are the products represent a condition of higher entropy. So we can just write it down. Reactants NaHCO3 is a solid and it has low entropy. Among products there are one solid and two gases, therefore the product represents a condition of higher entropy. So the fourth we have here is that is H2, that is in the form of gases, and that gives 2H in the form of the gases. Here one molecule gives the two atoms, and that is the number of the particles increase, leading the more disordered state, and 2 moles of hydrogen atom and a higher entropy than one of the dihydrogen molecule. So we can just write it in that only. So here one molecule gives two atoms, that we can say that the number of particles increases, leading to more disordered state. Then 2 moles of H atom, that is hydrogen atom, have higher entropy than 1 mole of dihydrogen molecule. Okay, so we'll go ahead with another question, and that is also an important question here, as you can see. So for the oxidation of iron here, that is a 4Fe, that is in the form of solid here, and with regard of that plus that is your 3O2, that is in the form of gaseous state, it gives 2FeO3, that is in the form of solid. Entropy change, it will be minus 549.4 kilojoule, and that is your mole inverse at 298 Kelvin here. In spite of a negative entropy change of the reaction wise, the reaction is spontaneous. So delta R of enthalpy that they had given for the reaction is minus 1000, which is minus 1648 into 10 to the power 3 joule mole inverse. This is the question what they had given you here. So according to that, one decides the spontaneous of a reaction by considering the delta S, that is total, which we had read just before that, and that is S of system, and delta S of system, and as well as delta S of surrounding. So for that, for calculating the delta surrounding, we have to consider the heat absorbed by the surrounding, which is equals to minus R of del H, and that at temperature T, the entropy change of the surrounding, we can say write it down delta S, that is of surrounding, and that is equals to delta R, R of H here, and that upon T, and that constant pressure, and that will be minus 11648.1 10 to the power 3 joule mole inverse. that will be upon 298 Kelvin, and for that we'll solve this further, and then we'll find out 5530 joule Kelvin inverse mole inverse. That's the total entropy change for this reaction would be. And after that, for finding out the another things that we are calculating here in reference to this, that we can say that like delta H total, if I'm talking about, so delta S total, that will be equals to what we had find it out, that is 5530, and that it will be plus add on minus 549 and 0.4 joule Kelvin inverse and mole inverse. So we'll add on, and then we'll get 4980.6, and that is joule Kelvin inverse and a mole inverse here. And for that, thus as this shows that the above reaction is the spontaneous here. According to this, we'll move ahead with another heading, that is your Gibbs energy and the spontaneity, and that we have to discuss. This is the C part of this particular thing. So here the Gibbs energy and the spontaneity, if I'm talking about, so we can see that from the system, it is the total entropy change, that is of delta S total, which decides the spontaneity of the process. But most of the chemical reactions falls into the category of the either closed system or open system. Therefore, for most of the chemical reaction, there are changes in the both enthalpy and the entropy, and it is clear from the discussion that the previous section that neither decrease in the enthalpy nor increase in the enthalpy alone can determine the direction of the spontaneous change for that system. For this purpose, we can define a new thermodynamic function for the Gibbs energy, or the Gibbs function, that is denoted by the G equals to H minus of Ts, and that Gibbs function where G is an extensive property and a state of a function, and the change of the Gibbs energy for the reaction of delta G, that we have written delta G system here, that is of, we can say, write it down, delta G is system here, that is equals to delta H of system minus, that is T of delta S system minus, and S system here delta T. So at a constant temperature, if I'm talking about that constant temperature, we are talking about delta T equals to 0. We can find it out, the delta that is delta G system, and that is of equals to delta H system and T of delta S system here. And with regard of this, usually the subscript system is dropped, and simply we can write it down the equation, that is delta G equals to delta H minus T of delta S here. This is reducing the subscript here. And with regard of that, Gibbs energy changes equals to the enthalpy change minus the temperature multiplied by the entropy change, and that is referred to the Gibbs equation, one of the most important equation in the chemistry. And here we have considered both the terms together for the spontaneity energy in the terms of the delta H, and the entropy delta S, a measure of the disorder as indicated earlier. So dimensionally, we can say that if we analyze, we find that delta G has a units of energy, because both delta H and the T of delta S, the energy terms in the sense of T, we can say write it down that T delta S equals to kilojoule, that is sorry kilo, and that is a joule by Kelvin, that is equals to joule only. So where we can see that now, because let us consider about the delta G, that is related to the delta S total equals to delta S system plus delta S surrounding, and it is the system that is a thermal equilibrium with the surrounding. Then the temperature of the surrounding is the same as so that the system, and also increase in the enthalpy of the surrounding is equals to the decrease of the enthalpy of the system, and therefore the entropy change of that surrounding, we can say that delta S surrounding is equals to delta H of surrounding upon T, and that is equals to minus delta H of system upon T, that we can represent it here. And with regard of this, that delta S total, we can say that equals to delta S system plus minus delta H of system upon T here. So rearranging this equation, we can write it down here. As you can see that rearranging these equation, we can set right now temperature, that is of the total, and equals to T of delta S system and minus delta H of system here. For the spontaneous reaction, we can say that as the total is greater than that is greater than 0, and that delta S system minus delta H system is greater than 0, and minus delta H of system minus delta S of system, that is also the greater than 0. using these equation, the above equation that we are using it, so that we can get that minus delta G equals to greater than 0, and that is we can say, right, delta G equals to delta H minus delta T of delta S, that is less than 0 here. Okay, so here the delta H system is the enthalpy change of the reaction, and the T of delta S system is the enthalpy which is not possible to use using. So here with this regard of minus delta G that is greater than 0, so with this, and the delta G is equals to delta H minus D delta S, that is less than 0 here. So with this, the delta H system is the enthalpy, that is change of the reaction of delta T delta system, as an energy which is not available, do not work. So where the delta G is the net energy available to do useful work, and thus we can say that we can measure these of the free energy, and for that reasons it is also known as the free energy of that reactant. And with regard of this, if I'm talking about delta G, that gives a criteria for the spontaneous constant pressure and time. And there are the two points related to this, that is if delta G is negative, अगर delta G जो है वो आपका negative है, okay, then of course yeah negative है, it means that is less than 0, and the pressure the processes is spontaneous, तब आपका जो process होगा वो आपका spontaneous होगा. And अगर आपका delta G, if here, and so if here also, if delta G is positive, okay, and that is means that is greater than 0, so the process is non-spontaneous. Okay, so you have to understood with this, and note, you can just write it down. If the reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when T delta S is large enough to overweigh delta H, and this is happens in the two ways. That first is if the positive entropy change of the system can be small, in which the case T must be large, and the second case that it possible is the positive entropy change of the system can be large, in which case that T may be small, and the former is one of the reasons why reactions are often carried out in the high temperature, and that what we will see the effects of the temperature on the spontaneous reaction as well. With regard of this, if I'm talking about, so here the Gibbs energy change and the equilibrium that we will have to discuss here is Gibbs energy change and equilibrium, if I'm talking about. So we have seen how the knowledge of the sign and the magnitude of the free energy change of that chemical reaction. So where the first is prediction of spontaneity of a chemical reaction, and the second is prediction of the useful work that could be exacted from it, extracted from it. So with respect to that, so far we have considered free energy changes and the irreversible changes, and let us now examine the free change, that is change in the reversible change. If I'm talking about the reversible change, so reversible under the strict thermodynamic sense is a special way of carrying out the process such that the system is at all the times as perfect equilibrium with its surrounding, and when then applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up, and this means that the reactions in both the directions should process with a decrease in the free energy, which seems impossible, and it is possible only when, if I'm talking about, so in the case of the reversible under the strict thermodynamic sense, that a special way of carrying out a process such that the system is in all the time is perfect equilibrium, as I told you, with its surrounding as well. When it applied to a chemical reaction, the term reversible indicates that a given region can proceed in either direction simultaneously, and so that the dynamic equilibrium is set up. And this means that, so now with regard of that, how with regard, if I'm talking about that, this means that the reaction in the both directions should be proceed with a decrease in the free energy, and which seems it possible. It is possible only if the equilibrium at the free of free energy of that system is minimum, and if it is not, the system would spontaneously change in configuration of lower free energy. So the criteria for that equilibrium we have is A plus B, and that gives the C plus D as well as C plus D, that reverse to give A plus B here. For that, delta R of G is equals to 0 here. For this Gibbs energy for the reaction in which all the reactants and the products are in the standard state, and delta R of G enthalpy is related to the equilibrium constant of that reaction. So we can just write it down, 0 equals to, that is delta R of G enthalpy plus RT log n K here, and that is delta R of G. If I'm talking about delta R of G, so we'll write it on minus RT log K, and delta R of G, that is equals to minus 2.303 RT log K here. With regard of that, we also know that delta R of G is equals to delta R of H minus T delta R of S, that is equals to minus RT, which we had find it out, minus RT log K here. So we can write it down like that also. For the strongly endothermic reaction, the value of the delta R of H here, that may be large, and as well as the positive, and in such cases value of K will be much smaller than a 1, and the reaction is unlikely to form much product. And in the case of exothermic reaction, delta R of H is large and negative, and delta R of G is likely to be large and negative too. In such cases, K will be much larger than 1, and we may expect these strongly exothermic reaction to have a large K here, and hence I can go near completion. As well as delta R of G, if I'm talking about, this is also depends upon the delta R of S here. If the changes in the entropy of the reaction is also taken into the account, the value of the K or extent of the chemical reaction will also be affected dependent upon the whether delta R of S is positive or negative here. With regard of this, we can conclude some of the information regarding this. So we can just make a table, a sort of a table effects of the temperature and the spontaneity of the reaction here. Here we can just write it down, delta R of H and that enthalpy, and that is delta R of S enthalpy, and then delta R of G enthalpy. And we'll just gone through a description. I will tell you the description, will not write it down, but yes, of course I will tell you here. So with regard of this, if I'm talking about the description, as I will tell you, as I told you. So here this is a sort of a table which is making the effects of the temperature on the spontaneity of the reaction here. If I'm talking about delta R of H, अगर ये negative है और delta R of S plus है, and delta R of G जो है, that is also a negative here. So here with the description, So what it is possible that reaction spontaneous at all the temperatures, then it will be the possible fact that will be given at अगर डेल्टा आर ऑफ एच नेगेटिव है और डेल्टा आर ऑफ एस नेगेटिव है then the for the delta r of h that is also negative but it could be at a low temperature here and the reaction spontaneous at a low temperature here. And with regard of that delta r of h, this is negative, and if the delta r of s also negative, and then this will be the plus, but this is at a high temperature here. Okay, so this is at a high temperature, and for this the reaction non-spontaneous at a high temperature. With regard of delta r of h, अभी यहाँ पे negative negative हो गया, like we are going for positive. It is delta r of s is also positive, then we will get plus here and at low temperature. So it will give a plus at a low temperature here, and for that a plus at low temperature. Reactions non-spontaneous at a low temperature here. So we'll go ahead with another one, that is if delta r of h is that is positive and delta r of s is positive, so the delta r of g will be giving negative because at a high temperature. Okay, and of course when it will be the positive and it will be the negative, so it will give as positive. With this, if I'm talking about the reaction is spontaneous at a high temperature, and for this that at all temperature, so it will be the reaction non-spontaneous at all the temperatures here. So this is all the description that what we had talked about is effects of the temperature and the spontaneity of that reaction here. Here it is we can say that it is possible to obtain an estimate of delta r of g enthalpy from the measurements that of delta h subscript that we have written here. So where delta G from the measurements of delta H enthalpy and the delta S enthalpy, and they calculate K at any temperature for economic yields of the product. And for the second point, if K is measured directly in the laboratory, value of delta G of enthalpy at any other temperature can be calculated. So let's go ahead with a question that we have to solve here. That is, calculate delta R of G for a conversion of oxygen to ozone, that is C/2 O2 gas that gives O3 gas at 298 Kelvin if the Kp for this conversion is 2.47 into 10 to the power minus 23 here. According to this, we know that delta R of G जो है enthalpy that we have given minus 2.303, जो कि हमने अभी already पढ़ा था इससे 2 मिनट या 5 मिनट पहले. So that will be here, and for that sake that R they had given you here, and that will be the 8.31 that we know very well, that 8.31 of 4 joule Kelvin inverse mole inverse, and therefore delta R of G हम निकालेंगे. So we'll go ahead and we'll find it out. Delta R of G enthalpy we will be finding out, that will be equals to minus 2.303, that is multiply 8 point, क्योंकि RT था तो R is 314 J kilo Kelvin inverse and mole inverse. And if I'm talking about the temperature, so they had given you 298 temperature, so we'll multiply that also. That is 298 Kelvin, and log आपका जो होता है that is they had given you already the conversion, that is 2.47 into 10 to the power that is minus 20, here is 29, and when we'll multiply, we'll solve this further, so we'll get 16300 and then 0 joule mole inverse, and we'll convert into the kilojoule because joule में दिया हुआ है, so we'll convert it to that is will be the 163 kilojoule mole inverse here. Okay, so this how you can find it out, delta R of G, and calculate the conversion of the oxygen to the ozone what they had given you at 298 Kelvin, and that the conversion they had given you here for the Kp. Moving ahead with another question, and that is your question that is your find out if I'm talking about the find out the value of equilibrium constant for the following reaction at 298 Kelvin. The reaction we have is 2NH3 of gas plus CO2 that is in the form of gas, that gives NH2CO NH2 aqueous solution plus H2O that is in the liquid, and vice versa, NH2CO NH2 plus H2O that gives 2NH3 plus carbon dioxide. And here the standard Gibbs energy change, delta R of G at a given temperature, that is minus 13.6 kilojoule mole inverse. For this we have to solve and we have to find out the solution here, and the solution is as follows. Here with the reference to the solution, so we know that log k is equals to minus delta R of G subscript upon 2.303 RT here. So we'll put the value here and we'll find it out. That will be okay. I'm putting out here because it is a long value here. That is 13.9 minus 13.9 into 10 to the power. Okay, that we will go ahead. The value is 13.6 into 10 to the power 3 joule mole inverse, and then upon what we will get is 2.303, and that is multiplied by R and T, and that is R is 8.314 joule Kelvin inverse and mole inverse, and that multiplied by temperature, that is 298 Kelvin has been given here. And while solving this we'll find it out, that is your 2.38, and hence K, that Kelvin is anti-log 2.38 का अगर एंटी लॉग निकालेंगे we'll get 2.4 into 10 to the power 2 here. So we'll find the solution, and now moving ahead with the next question and as well as the last question of the session as well, and we'll come here, we'll after completing this we'll complete the thermodynamics chapter as well, and in the next class we'll start with the equilibrium. So the question we have is at 60 degree Celsius, dinitrogen tetraoxide is a 50% dissociated. Calculate the standard free energy change at the temperature and at 1 atmosphere. According to this, we can just find out the reaction. First I will just writing out the reaction, that N2O4 in the gaseous form, it will give 2NO2 in the form of gaseous state, or we can say that 2NO2 gives N2O4 here. And the same way, if N2O4 is 50% dissociated, the mole fraction of the both the substance is given by, we can just write it down, X of N2O4, and that it gives 1 minus 0.5 upon 1 plus 0.5, and that's why we can say that X of NO2 अगर हम बात करते हैं, so we will be finding out 2 into 0.5 upon 1 plus 0.5. After solving this for the P, N2O4, we can just say that 0.5 upon 1.5, and that is multiplied by 1 atm. And so for P N of 2 अगर हम बात करते हैं P of NO2 की अगर हम बात करते हैं, so we'll get 1 upon 1.5 multiplied by 1 atm. So the equilibrium constant for the Kp, if I'm talking about and finding out Kp, so we'll have P of NO2, and that is of square upon as well as P N2O4, and that it will gives 1.5 upon 1.5 ka square, and that is multiplied by 0.5 here. According to that, by solving this we'll get 1.33 atm, and since we are finding out the delta Rg here, so we'll delta Rg, we will be getting it minus RT, and that is ln Kp, and when we are finding out delta Rg here, that will be minus 8.314 joule Kelvin inverse and mole inverse as well, and that is multiplied by 333 Kelvin here, and that is also multiplied by 2.303, and then it will be multiplied by 0.1239 here, and it will gives you as answer that a delta of R of G here is minus 63.8 kilojoule or mole inverse. So this is the answer that we'll find it out. And for this sake, if I'm talking about in reference to the chemistry what we had discussed here, in the reference of this we had discussed the unit 1 as well as unit 2 as well as unit 3 as well as unit 4 in the regard of all these questions. So we have completed the unit 1. Here we had some basic concepts of the chemistry, where we had discussed about the importance of chemistry, nature of matter, properties of matter and their measurements, and uncertainty in the measurements, laws of chemical combination, Dalton's atomic theory, and the atomic and molecular masses, mole concepts and molar masses, percentage composition and stoichiometry and the stoichiometry calculation. In the unit 2, if I'm talking about the structure of atom, that is important a unit as well. Subatomic particles, atomic models, a development leading to the Bohr's models of the atoms and Bohr's models of hydrogen atom towards a quantum mechanics model of the atom and quantum mechanical model of the atom as well we had discussed in the unit 2. For the unit 3, we had discussed the classification of elements and the periodicity and the properties, and that is why do we need to classify elements, genesis of the periodic classification, modern periodic law and the present form of the periodic table, nomenclature of the element with atomic number that is greater than 100, electronic configuration of elements on the periodic table, electronic configuration and the types of element that is S block, P block, D block and F block, periodic trends and the properties of element that we had discussed here. And after that if I'm talking about some more topics and some more units we had discussed here as follows. So in terms of unit 4, chemical bonding and the molecular structure, we had done Castle-Lewis approach for the chemical bonding, ionic and the electrovalent bond parameters, the valence shell electron pair repulsion, that is the spur theory, valence bond theory, hybridization, molecular orbital theory, bond in the some homonuclear diatomic molecules, and the hydrogen bonding as well. Then we had discussed unit 5, that is states of matter, that is intermolecular forces. So in regards of the chemical bonding and the molecular structure, the Castle-Lewis approach we had discussed to the chemical bonding, ionic, electrovalent and bond parameters, the valence shell electron pair repulsion theory, and that is the super theory, valence bond theory, hybridization, molecular orbital theory, bonding of the some homonuclear diatomic molecules, and the hydrogen bonding. As I told you, states of matter के बारे में, intermolecular forces and thermal energy, intermolecular forces and versus thermal interactions, the gaseous state, the gaseous law, ideal gas equations, kinetic molecular theory of the gases, behavior of the real gases, that is deviation from the ideal gas behavior, and the liquefaction of the gases as well as the liquid state that we had discussed in the unit 5 here. Moving ahead with the unit 6 जो कि आज हमने complete कर लिया है, that is of thermodynamics. इसमें हमने thermodynamic state applications, measurements of delta U and delta H of calorimeter, enthalpy change, delta R of H of reaction, enthalpy for the different types of reactions, spontaneity and the Gibbs energy and the change in equilibrium that we had discussed here. With regard of that, equilibrium की बात करते हैं तो this is unit 7 here. Equilibrium in the physical process, equilibrium in the chemical process, dynamic equilibrium, law of chemical. So here we had done equilibrium in the chemical process, dynamic and equilibrium, law of chemical equilibrium and the equilibrium constant, hormone equilibrium, heteroequilibrium and application of the equilibrium constant, relation between the equilibrium constant K, reaction quotient and the Gibbs energy G, and the factors affecting equilibrium, ionic equilibrium in solution, acid, base and salts, ionization of acids and bases and buffer solution and solubility equilibrium and the strongly soluble salt that we had discussed. So class अगर आप हमारे channel first time देख रहे हो, it's a huge request कि आप हमारे channel को subscribe करो, like करो, share करो, so that many and maximum people can achieve that, and you can also use this. Please like, share and subscribe our channel. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.